It's a pleasure to be here with you. I'm Rosalind Picard. I'm thesis advisor for Natasha Jakes, and this is a very happy, hopefully, occasion where Natasha is going to be presenting the defense for her thesis, quite a large body of work. So we're going to get started. She's going to present for probably a little bit more than 45 minutes. Then we will open it up to Q&A to the audience. If you have to ask a clarifying question as we go, that's fine too, but we want to save real conversational discussion questions for the end. Then probably after about 20 to 30 minutes of public back and forth, we will chase out the public and the committee will meet with Natasha. After that, if she's determined to have passed her defense, there will be a small celebration in our group around the corner back over there, to which all will be invited. And I'm sorry, Doug and Nando won't be able to come for that part. So without further ado, you've got a mic on.
Yes.
Okay, and are Doug and Nando both?
Nando has joined, but Doug is still joining. Oh, Doug's here, okay.
There they are, great. Hey guys, thank you for joining us. All right. Let's get started. Thanks.
Thank you so much, Roz. I'm excited to be here. Wow, thank you guys so much for coming. This is great. And if you're wondering who Doug and Nando are, I just want to mention thanks to my committee for being here. So Roz is my advisor. Doug Eck and Nando DeFreitas are at Google Brain and DeepMind, and Joelle Pinot is right here. She's from FAIR and McGill. So very excited that they're able to join us as well. I've been studying the problem of machine learning for the last 5 years here at MIT. And if you know me at all, you'll know that I'm very willing to jump into an excited rant about how amazing machine learning is and how we're making so much progress and it's so exciting. And I'm not the only one. Interest in machine learning and in particularly deep learning has been exploding over the last few years because we've been able to tackle new problems that we weren't able to tackle before. And so, I'm very hyped about this. But we know that there's still huge problems with these techniques. So one of the biggest problems is generalization. So these models can be pretty brittle. If you train a model to play an Atari video game that looks like this, and you just slightly switch the colors, it just collapses. It can't play the game at all anymore. And that's just a far cry from a model that could play this video game and this one at the same time. So we know that these models are not good at generalizing to new problems. So this is particularly a problem in reinforcement learning, which is an area that I'm really excited about. And even though we've made impressive progress in reinforcement learning in the last few years, like we've beaten the world champion at the game of Go, a human champion, again, generalization is still a problem. So one way to overcome this is to think about intrinsic motivation for reinforcement learning. So this is where you design a reward function that the agent is trying to optimize that's environment agnostic, and it could cause this agent to learn across many different tasks. So a couple of areas where we can develop intrinsic motivation are, for example, curiosity. So if an agent is driven to discover novelty in its environment, then perhaps it will learn across many environments. Similarly, empowerment rewards an agent for having high mutual information between its own actions and its future state. So basically, it wants to be able to manipulate the environment. It wants to have power over the environment. But if I look at this, I think the things that motivate people aren't limited to a drive for novelty and a drive for power. So what else motivates people? I would argue that people are very motivated by other people. So if you guys were looking at me like this audience here, I would be extremely motivated to go to the next slide. So humans are really good social learners. I would argue that social learning is a key component of why humans are so smart. And if you don't believe me, I've thrown up a lot of citations here that argue that social learning not only drives our cognitive development, but is actually tied to our ability to transmit knowledge and evolve culturally, which is probably why I'm standing here talking to you about deep reinforcement learning, for example. So the focus of this thesis is broadly about how to incorporate forms of social learning into AI agents. And the first project I'm going to talk about is a multi-agent project. So there are multiple AI agents. How could we develop a form of social learning among the agents? And in this project, we wanted the agents to be able to learn socially from each other, but still train independently. And so we chose to do this by giving them intrinsic social motivation for having a causal influence over the actions of another agent. So why do we do this? Well, If we focus on learning from other agents' actions, then we don't need to observe the reward they're getting from the environment. And we think this is a more realistic assumption when we think about applications for these types of systems, like autonomous driving. So with autonomous vehicles, there's likely to be cars that are manufactured by Tesla and Waymo, and the Waymo car isn't going to be willing to share its proprietary reward function that it's optimizing with the Tesla car. So how could those cars still learn from each other just by observing what they're doing in the environment, such as whether they turn left? So that's the idea here. And we'll show that this causal influence reward is actually related to rewarding the mutual information between agents' actions. And we have the intuition that this will help agents learn more coordinated behavior with each other, so they'll learn to coordinate better. So how do you do that? That's all fine, but how can we actually make this work? Well, what we do is we start with a standard reinforcement learning agent that's inputting something from the environment, and it's having a recurrent module that it can understand what's been happening in the past. It's outputting a policy about how to act in the environment. And then we equip it with an extra model, and we're calling this a model of other agents. And what this model is doing is it's predicting the actions of the other agents. So it predicts at the next time step what every other agent is going to do, conditioned on the agent's own action. So what does that allow it to do? Well, it's actually able to then simulate counterfactual actions that it could have taken. So it can retrospectively ask, given everything that was going on at this moment in time, what if I had taken this other action instead? What do I predict would have happened? So it can ask itself, what do I predict this other agent would do if I had done this action instead? And then what that allows it to do is it can sample a bunch of counterfactual actions that it could have taken, think about all the things it could have done, plug that into its predictive model and sum over that to get this policy of the other agent, what the other agent would do if it wasn't considering this agent at all. It's sort of default policy. And the divergence, the difference between the other agent's default policy and its policy conditioned on this agent's action, is a measure of the causal influence of this agent's action on the other agent. And the idea is to give this as a reward to agent A. So the agents get a reward if they influence the behavior of another agent. And if you don't believe me that it's the causal influence, that's what this cool graph is for. So we know from Pearl's notion of causality in directed graphs that causality can't pass on between an unconditioned collider node. So the only causal path is this path that goes forward in time between this agent's action at time step t and agent B's action at time step t plus 1. But we can also show that this influence reward is related to the mutual information between agents' actions. So this is the formula for the mutual information here. We see that it requires summing over the probability of the state, for example. But as we sample many random trajectories from the environment, we actually, in expectation over those trajectories, recover this mutual influence reward. So influence is the mutual information in expectation. So we think of this as a novel form of social empowerment. If you remember, empowerment was the mutual information between an agent's action and its own future state, and this is the mutual information between multiple agents' actions. But I'm going to stop here. Does anybody see a problem with rewarding an agent for causally influencing the actions of another agent? Getting a couple smiles. What do you think? Does an agent, in order to influence another agent, does the agent always have to help the other agent? So not necessarily, right? So it might be possible for me to just get in your way. You have to walk around me. I haven't helped you, but I've influenced you. So how do we make sure that the agents are influencing each other in a cooperative way? Well, we took two approaches to solve this. The first is that we tested this reward in environments where cooperation is precisely the hard problem. So we have these two environments. The first is called Harvest. It's a tragedy of the commons environment. So what agents are trying to do is pick up these apples, and they get a reward for doing so. But if they greedily harvest the apples too quickly, then the apples will be depleted, they won't grow back, everyone's going to go hungry. So even though each agent wants to harvest more for themselves, if they all follow that strategy, everyone loses. So it's a sequential social dilemma. It's meant to mimic like a spatially and temporally extended prisoner's dilemma. This environment is similar. It's called cleanup. Agents can make apples appear by cleaning this river, but it's partially observable. So when they're doing this, they can't actually see if these apples are appearing. Other agents can easily just exploit them by kind of stealing their apples. So to make that more concrete, what we're looking at here is called a Schelling diagram. And it's describing the payoff that each agent can get for following, for example, a defecting or exploitative strategy in red, or a cooperative strategy in blue, depending on the number of other agents out of 5 that are cooperating with it. So if everyone's cooperating or if no one is cooperating. And you can see that the agents are always going to get a higher payoff if they defect on their fellow comrades here. But of course, if everyone follows that strategy, again, everyone loses. So these types of long-term trade-offs over repeated iterations are very hard for vanilla RL algorithms to solve. In fact, they basically can't. But what we see is that when we add this reward for agents having influence over each other or having high mutual information, we see that the collective reward obtained by all of the agents is higher. And that means basically it's not any given agent that's doing better, but all of them are doing better together in this environment, meaning they're harvesting sustainably, for example, and it's evidence that they're cooperating. But how are they cooperating? How is this influence reward leading them to cooperate? Oh, and I should mention this actually does beat previous work. So this previous work, agents were able to view each other's reward function, and we actually see superior performance just from this influence reward. But how does it work? So let's check this out. So in this video, we have this purple agent here is the only one that's been trained with the influence reward. And you can see that it behaves a little bit differently than the other agents. So when there are no apples, the other agents keep exploring to try and find apples. But the purple agent is holding still. And in fact, it only ever used 2 moves to navigate the map, and it only ever traverses the map when there are apples present. So if it's moving, there must be apples. How does that allow it to gain influence? Well, if we take a look at a moment of high influence between the purple agent and this yellow agent here that can only see what's in this partially observable box, we see that there's this delicious apple that's outside of the view of this agent. But when the purple agent chooses to move towards the apple, which it only moves when there is an apple, that communicates something to this agent that there must be food present. It changes its intended behavior, and this agent is able to gain influence. So that's really interesting. And then we see something like that happening again. So here, this pink agent here has been cleaning the river. It can't see if any apples have appeared. But when this agent chooses to stay still, that signals that no apples have appeared, again changing its intended plan, and the agent gains influence. So what we see is that this influence reward has led the agent to learn to use its actions to communicate about the presence of food in the environment. So you can think of it like a little bee waggle dance. So we thought this was quite exciting. And so the next thing we did was to train explicit communication protocols with this influence reward. So what we're doing here's our normal policy for acting in the environment. And this is a policy that says which of several communication symbols the agent should choose to emit and show to the other agents at the next time step. So it's kind of this cheap talk communication channel. I can say something, nobody else has to listen to it. The agents are free to ignore that channel. And the idea is that we're going to train this communication policy with the influence reward. So agents get a reward if something they say influences the behavior of another agent. And we think that this actually overcomes the problem of the influence not being beneficial. Because the only way an agent that is acting in the environment to maximize its own reward is going to change its behavior based on a communication symbol that it's free to ignore is if that symbol is going to reliably help it achieve its own environmental reward. So we think that influential communication should benefit the listener. That's our hypothesis. So how well did this work out? Well, I should at first point out that cheap talk between self-interested agents actually doesn't work. So we can show theoretically that as agents' interests diverge, the amount of information placed on the channel goes to 0. And we can show empirically in past work in multi-agent reinforcement learning that agents that are self-interested don't learn to use these types of channels effectively. But we see that when we add this influence reward, the agents achieve, again, higher collective return, suggesting that it is helping them to coordinate. And we also see that the communication protocols they learn are more meaningful. So agents are speaking more consistently about what they're doing in the environment, and they're also having high mutual information, as we suspected, when there are moments of influence, although that is a very sparse occurrence. But this is my favorite slide. So what you're looking at here is the degree of influence between an influencer agent and an agent being influenced and their individual returns. And what we see is that agents that are more easily influenced, or a better listener, if you will, tend to get higher individual environmental reward. And this is a reliable finding across many different hyperparameter settings, hundreds of examples of these environments. So this seems to support our hypothesis that the information being sent over the channel is helping agents to achieve their own environmental reward. So this is to make Joelle happy. So this slide is to show that these results are reliable. We ran it not only for 5 random seeds for each hyperparameter setting, but for the top 5 hyperparameter settings, and we see consistent performance improvements from this influence reward. I do want to mention that there are some caveats. So we talked about whether the action-action influence is going to help the other agent is going to depend on the environment, on the hyperparameter settings. We think that one of the reasons that communication emerged in this setup is that agents were trying to maximize both their environmental reward and their influence. And actually just communicating information may be one of the cheapest ways to gain some influence without deviating too much from your optimal policy in the environment. We think that influence on self-interested agents via this cheap talk channel should benefit the listener, but that depends on agents that are interacting repeatedly. So if in some future work there was some agreed upon communication protocol that agents could use to communicate with a new agent that they would never see again, they could potentially lie and still gain influence. But of course, if you're playing with the same agent over and over and they lie to you, you're not going to trust them and they will lose influence over time. So in conclusion, we think of this social influence as a unified method for promoting coordination and communication in multi-agent settings. And this allows the agents to learn socially from each other, but train independently. And that's actually a big improvement over prior work in Marl, which often relies on agents viewing each other's reward or having a centralized controller that teaches all the agents something. So we think this is nice. So that's everything for this project. I want to stop right now if anyone has a question. Clarification, yes?
For the independence of agents, do they have to infer each other's actions? Or do they still have access to that as like information?
Yeah, so we make the assumption that agents can observe each other's actions. But actually, in the final product, we ended up saying that you can't influence an agent that you can't see. That's not within your partially observable view of the world. So we think that's more reasonable. Yeah.
Also via the communication channel.
The communication messages are always sort of heard. Even if you're outside of the view, they're transmitted to all the agents. Yeah, which we again think is pretty reasonable.
What is the dimension of this communication channel? Is it like 1?
We vary the dimensions, I think, between like 10 symbols and 20 symbols, so pretty small. But they can actually, the interesting thing about this that we didn't get a chance to analyze is they could potentially communicate compositional messages. So if I say AAB, that might mean something different than AAC. And actually, the metric that we have of the communication doesn't account for that. So it would be nice future work to more deeply analyze how the agents are communicating.
Yeah, see what each unit does.
Mm-hmm. Exactly, yeah.
Awesome.
Other questions about this project? Okay, let's move on to the next one. We can always take more questions at the end. So I'm really interested in this idea of social learning because I think it's really powerful. But it seems like the best and smartest things you could learn from in your environment are going to be humans. For most tasks that we want an AI to do, like for example, just recommend us music, humans are going to know better how to perform the task. And I'll give you a motivating example why learning from humans could help. So this is a real conversation between a user and their Alexa device. Alexa, what's the right way to Walmart? The right way to spell Walmart is W-A, blah, blah, blah. So I would bet you that when this mistake happens and Alexa doesn't meet the need of this person, the way they're going to respond is going to contain some element of frustration. Whether it's their tone of voice, the words that they use, there's a signal there that Alexa could be using to understand that she did the wrong thing and she better not do it again. So wouldn't it be cool if we could pick up on these signals and learn from them? And this is important not just for making deployed systems like Alexa more useful to people, but I would argue it's important for long-term considerations of AI safety. Because if these models are able to sense accurately our preferences and adapt to them, then they're going to be more likely to take actions that are aligned with our preferences. But the problem is that people don't actually enjoy manually labeling their preferences. So nobody actually wants to fill out these cards. How many people have ever trained the Google algorithm by filling this out? Okay, I've got a few hardcore people. Thanks, Dad. Good job. I think most people don't actually enjoy doing this. But in contrast, social feedback is rich and ubiquitous and natural. You're already making facial expressions. You're already having a tone of voice. Couldn't we pick up on this? So how many people have ever used a frustrated tone with their Alexa or Siri or yelled at their Roomba? Okay, so there's some signal there. So that was the focus of this project. So we wanted to make an AI agent that could sense human preferences. And here we wanted to sense this in text. So here's an example of me talking to a conversational AI, a chatbot, and you can see that we have this state-of-the-art sentiment detector that was actually developed here in the Media Lab that can tell that when I say something like, "that didn't make sense," that's a negative sentiment. I'm not happy. So couldn't we use this as a reward signal to disincentivize the agent from whatever it just did? Similarly, when the conversation is going well, it can detect that I'm happy and the agent is doing something right. So that's the idea behind this project. I worked on this project with a number of wonderful collaborators in this group, including Asma and Judy, and I'll talk more about that later, and Craig, Agata. But we ended up building this whole platform to allow people to chat online with our bots and collect this human interaction data. And so our hypothesis, even though in that interface, we allow people to manually tag the bot's responses as good or bad using this upvote, downvote, we think that learning from these explicit manual ratings is not going to scale as well as learning from these implicit cues like the sentiment. And so the implicit cues we focused on in this work were not only the sentiment of each utterance as well as over the course of the conversation, but even whether we could get the user to laugh, how much they typed ha, how many words they typed, how long they bothered to talk to the bot, because we reasoned that if it's totally terrible, you can't really put up with talking to it for too long. And we also rewarded the distance in embedding space between the bot's answer and the human input to help it stay on topic. So these are rewards that are elicited from interacting well with a human. They were based on some research into the psychology of what makes a good conversation. And based on that, we also added a reward for asking questions, because apparently this is an important active listening skill. But the issue with this reward, of course, is it's totally in the bot's own control whether it asks a question. So it's kind of trivially exploitable. So we'll see how well that works out. So what we're trying to do here is take this big conversational AI model that takes in some text and outputs a response and train it with reinforcement learning. And this is actually a really challenging problem because normally in reinforcement learning, the number of actions you can take, like in the previous project, is on the scale of like 12 actions. But in generating language, there are 20,000 most frequent English vocabulary words that it can choose from for each step. So this becomes very difficult. And similarly, the state space is the space of all possible conversations. So that's also a little bit more complicated than the little grid world we saw in the last project. So that's difficult. And then trying to learn from human interaction actually presents its own problems. So here, we're treating the human as the reinforcement learning environment that we're trying to learn from. And when you're learning from human data, trust me, it's very painful and expensive to try to collect that data, especially if you're in academia. And so you basically want to salvage any little piece of data you got from a human, no matter how long ago you got it, no matter how different the model was or the data set, you need to be able to use it well. And so this necessitates really good off-policy reinforcement learning. And then the second problem is that you need to be able to test your model very carefully before redeploying to humans. You basically can't put some model on the internet and have it learning from its interactions with humans in a continuous way, or you might end up with some inappropriate behavior. So you basically have this atypical broken interaction loop where your RL algorithm, in contrast with normal RL, is not able to explore online in the environment to refine its estimates of how good certain actions are. And so this is called batch reinforcement learning, learning from a static batch of data without the ability to explore. And it's a very difficult problem that has only been explored a little bit. But I'll explain why it's tough. So off-policy learning is really hard for deep reinforcement learning. So most deep reinforcement learning algorithms are going to fail to learn if the data that they're trained on is not heavily correlated with the current policy. And secondly, even supposedly off-policy algorithms like Q-learning are going to fail to learn when they can't explore in the environment. So why is that? Well, let's look at the Q-learning optimization function. So what it's trying to do is it's trying to bootstrap an estimate of the total reward it can expect from taking an action in a certain state by looking at the reward it observed and then estimating the maximum expected future reward it can get in the next state. And if there's some part of the state space for which you don't have good data, so you have really noisy estimates, you don't have a lot of data, so these are kind of garbage estimates, what do you think is going to happen if you take the max over those noisy estimates?
It will go to a region where, because within noise there are very high outliers.
Yes, exactly. So the noise leads to a high outlier. It's not the real estimate. Here's the real estimate. Noise is making it higher. You take the max, it's going to persistently overestimate the value in that region of the state space. So it's exactly what you said. So Q-learning is optimistic in the face of uncertainty. If it hasn't seen a lot about this region, it thinks it's probably good. And that's actually amazing if you're doing normal RL and you're able to explore, because you have some bad estimates for some part of the state space, you're optimistic, you go there, you explore, you refine your estimates. So nice for normal Q-learning has this built-in exploration bias. But it's terrible if you're learning from a static batch of data, because you don't have data for this part of the state space, and it wants to go over there, and you have no data there to learn a good policy. So it's just going to drive itself out of the batch data for which you're able to learn. And so we'll see that happening if we just do this batch Q-learning kind of naively. So in the next few slides, I'll describe a couple of baselines to do batch Q-learning, and then we'll see how well they do. So firstly, we have to absolutely have all of our baselines at least pre-trained on some conversation data. So we want to take a pre-trained language model. And the reason we have to do that is our action space is 20,000 dimensional. We're never going to learn how to talk from scratch just by talking to humans for a few. Humans aren't patient enough to teach us that. So we take a bunch of known conversational dialogues, we pre-train a model, and then we fine-tune with reinforcement learning. The second thing we do is try to alleviate that overestimation bias with that max operator. So something that's been proposed in the literature is to do clipped double Q learning. So basically, you have two different independent networks that you use to estimate the total expected future reward, take the max with both of them, and then you take the min of their two estimates. But I think this is a bit clumsy, and it's also really expensive. Having two totally different networks is difficult, and how do you make them independent if you're initializing with a pre-trained network? So what we choose to do is to use dropout on our target Q network. So there was this finding in the literature that if you run multiple forward passes of a neural network trained with dropout, you actually get a Bayesian estimate of the uncertainty in the value the network is estimating. So we just take the lower bound of that to try to alleviate this overestimation. So those are our baselines that we came up with. We also adapted a baseline from the literature that was called batch constrained Q learning. What it does is it learns a generative model of the batch, P of A given S given the batch data, and then the RL algorithm is only allowed to act by sampling from that model. And the intuition there is it's not allowed to stray too far from the batch data. So those are our baselines. Can you guess how well they did? I guess I wouldn't be asking if it was that great, right? So here's an example of a conversation with this batch Q learning. And you see that it's not only, as we predicted, exploiting the trivially exploitable rewards, it's asking a question every single time, but it's also spamming the maximum number of tokens that it's allowed to spam, because that just gets more reward. I just said more things, good. But the other issue is that it's saying pretty unrealistic stuff. So where did you say to me is not a real sentence that should have been seen in the training data. So it's gone off into space, basically, as you were saying. So we see that it's diverged away from realistic natural language. Sorry. So how can we fix this? Well, our idea is we want to bake in an understanding of what is realistic language directly into the RL policy. So what we're trying to do here is not only optimize for the normal total expected reward over the trajectory as we would do in RL, but we want to minimize the divergence of our RL policy from our pre-trained language model. So that language model is saying, what's realistic looking language? Hopefully it knows that, where did you say to me is not a high probability sentence. So we want to make sure that our RL model can't stray too far from that. And if we look at the formula for the KL divergence, we can see that this amounts to just adding two simple terms to our Q action value function. So we add the log probability under the prior. So this is our language model. It says how probable is a given word given the sentence context. So it says, what's realistic language? Don't get too far away from that. We also subtract the probability under the RL policy itself. And that actually just amounts to doing entropy regularization. So that means your policy needs to be as stochastic as possible while still optimizing for the rewards. Well, why do we care about that? In dialogue, we don't want to collapse down to a single conversation. We want to have a lot of variety in the things that we're saying. And there's different ways to solve an entropy regularized Q function. So one is to replace that hard max with a log sum exp. So that actually also helps alleviate the overestimation. So these are the models we're testing, this KL control Q version, KL control psi, and then we also test a version of the psi with making a better language model by averaging several language models together. So let's check out how well this worked. So we conducted a human evaluation where we compared our baseline batch Q learning models to these KL control models on human ratings of quality, etc., as well as the votes that the models received in the interface for their various utterances, and the total reward they elicited from humans. So how much did the human express positive sentiment? How long did they continue speaking? This type of reward. And we see that while these techniques we're proposing do help, they improve over the baseline. We have this Monte Carlo averaging helps. The biggest difference comes from the KL control methods. So they actually significantly outperform the baselines, and we see big differences in terms of not only the ratings, but the votes and the reward they elicit from humans. We can see why this is happening. So this is the KL divergence of our RL models from our original language prior. So remember, we initialize the RL models with the weights of the language prior. So they start the same. But as you continue training, we see that those batch Q models diverge away from the prior. So they diverge from realistic language, and they're trivially exploiting those rewards. And we think this leads to very unrealistic estimates for our baseline. So when you sample from that prior and then you try to assess the values in Q-learning, it becomes less and less realistic, and it doesn't perform well. But in contrast, the KL control models are able to alleviate that effect and stay close to realistic looking language. So here's how it actually turned out. So you can actually go chat with these bots yourself. They're still deployed live. And we can see that the KL control model is using a bit more realistic language. You ask it, hey, what's up? It says, I'm not sure, but I'm glad to see you. We did notice that while it is realistic, optimizing for this positive sentiment did lead it to be extremely cheerful, polite, and supportive. So it's always saying things like, thank you, you're the best. So we actually developed some post hoc metrics to assess exactly how cheerful and polite these bots are by sort of counting things they say like, thank you, I'm sorry, etc. Maybe we're going to call this the Canadianness metric, I'm not sure. Here, what you're looking at here is all of the techniques that we trained and the Z-scored reward that they obtained, not only from the rewards they were trained on, shown in red, but these post hoc metrics shown in green. And what you can see is that, as we predicted, these batch Q models trivially exploit the easy rewards, like asking questions. But the KL control models have shifted their distribution to this polite, supportive, and cheerful language. And that actually allows them to elicit this higher human reward. So they have to do a more complicated thing, basically. And then we tested how well the different reward functions worked when we trained models with each reward function independently. And we see that actually the sentiment-based reward led to the highest quality conversation. So the affect is important in a good conversation, which is a really nice finding when you're in the affective computing group. We also saw that these models trained on implicit reward do score higher than training on these manual upvote, downvotes. So that helps validate our hypothesis that getting humans to manually label their preferences doesn't scale well. So in conclusion, this is the first work to propose using KL control from a pre-trained prior as a way to handle this off-policy, no exploration problem, batch RL. We proposed several enhancements that all work to varying degrees. We found sentiment to be the most valuable implicit reward, and we see that implicit signals are more scalable than explicit button presses in this case. All right, any questions about this work? Yes?
Do you have a comparison for like an equal number of sentiments and votes? Because like it's obviously more scalable completely, but like what's the actual signal like per implicit sentiment?
Right.
Explicit vote.
So arguably you get the sentiment no matter what, and then the explicit vote you don't get unless the human bothers to send it. So we just say that we have the same number of utterances, but people can voluntarily press the button. We encourage them to do that in the instructions. But yeah, I don't have the comparison of like, if we restrict only those utterances that were upvoted, downvoted to compare with the sentiment, maybe in that case, you would get better performance from manual upvotes. Part of the problem is that we just think people won't bother to do it. Yeah. Yes.
So I can imagine that some people like a happier Alexa and some people like a more, I don't know, sentimental Alexa, etc., etc.
Yes.
Can you train it by giving sort of the input
An extra parameter which you teach the agent to map to, for example, sentiment.
Yeah.
So that if you buy a new Alexa, I set happiness to 5. You get a very happy one.
Yeah.
It automatically doesn't have to relearn the whole policy through meta learning or so, but that automatically, is that possible? That you
Yes.
automatically get it to
So
be happier?
That's a great idea. And I think there is definitely something really interesting and deep there in how to respond appropriately, because actually just expressing positive sentiment isn't even good for the same person but across different contexts. So knowing how to respond emotionally at different times is a really challenging problem that we've only just started to dig into or think about. But also in terms of like each user having different preferences about how chipper they need their Alexa to be, I think that's definitely a good point. And having some personalization where you understand the user and adapt better to them could be really cool. And actually later in this talk I will talk about methods for personalization that I think could lead nicely into that. So thanks for your question. All right, yes?
Yeah, I have just a question about the implicit versus explicit. I'm wondering your thoughts on if there's like a spectrum of when explicit can be maybe more desirable, a human's more willing to do it. I'm just thinking of like, I train my dog and I'm like willing to say like, yes, you did a good job, yes, you did a good job, yes, you did a good job. And
Yeah.
I have a long-term relationship with this animal.
Yeah.
But similarly, if there's like an AI that I was like forming a long-term relationship with, maybe I'd be more incentivized as a human to like give it explicit kind of responses.
Yeah, and actually I'm really glad you asked that, because the next project we also look at implicit signals from facial expressions, and we think a lot about the interface and how the interface could be designed to elicit more feedback, basically. And I think there's something really rich there. But yeah, I think that's an interesting direction for future research, yeah. Okay, thanks. I'll go to the next project then. So speaking of that project, this was the same motivation, but here we want to actually learn from people's implicit signals from their face. So the way we did that, just as a quick description of this project, is we thought about which deep learning model is likely to generate samples that a person would possibly make a face at. And we landed on SketchRNN, which draws these cute doodles based on a sequence of pen strokes. And what we did was we showed those doodles to people and we collected their facial expression response. And then we trained this latent constraints model. So if you get the lingo, this is a GAN. Basically, it's a GAN on top of a VAE. So let me say that a little more clearly. This model already has a super cool representation of sketches that it's learned unsupervised by training on a bunch of sketches. What we want to do is we want to understand which parts of that representation space, these are sort of all the sketches you could possibly draw. These are all the sketches that are kind of realistic. We want to learn which part of the realistic sketches actually make people smile and make them frown less. So learn which part of the representation space to convert to. And then we apply this technique to helping this model learn to sketch better. So this is how the model used to sketch cats before our technique. You can see that there are some pretty good cats, but some of them are a little questionable. So as we train with only a small amount of facial feedback, this is a very sample efficient model. We actually only had like 70 samples of people smiling or not at this cat. We see that it learns to draw a significantly different type of cat. So we got these little cute mouths, we got whiskers, smiles. So whether drawing significantly cuter cats is a marvelous scientific achievement or not, I don't know. But if we look at the rhinoceros model, we see something interesting. So it turns out people, which is what trained this model, and this model are very bad at drawing rhinoceroses. So I don't know what this is, but it's not a rhinoceros, right? And what we see is that, again, training with only around 70 samples of facial feedback, the model has learned to draw actually pretty realistic looking rhinoceroses. So we actually think this is the first work to show that you can improve the quality of a generative model using facial expression feedback. And we did test this with humans, and yes, they do significantly prefer our model's sketches. So that was a foray into that. But the issue with all of these papers on learning from these implicit cues like facial expressions and sentiment is that if you want to be able to do that, well, you first have to be able to detect those signals. So facial expression detection and sentiment detection are kind of mature areas where we know the accuracy is good. But what are other ways we can actually detect these affective signals? So this was a focus of a lot of my early PhD. One of the papers I looked at was, can you predict if two people in a conversation are actually bonding with each other, whether they're having chemistry and rapport? And we do that using 1-minute slices of their facial expression and body language data. We actually get pretty high accuracy. But what I really want to talk about was a huge focus of my early PhD that I worked in close collaboration with a number of the people here, for example, Sarah Taylor, Ehi, Akane, and of course, Roz. So I've been going around giving this job talk and saying that this is Roz's dream, but I don't know, hopefully she's okay with me saying that. It also would be my dream. Yeah. So what we were aiming for here, what I think would be really cool, is to be able to take signals gathered unobtrusively from a person, maybe from their smartphone, maybe from a wrist-worn sensor like a Empatica sensor, send that to our server, do some super cool machine learning on it, and give people a personalized prediction of what we think their, people are laughing, that's a good sign, what we think their mood is gonna be like tomorrow. And we actually think this could be really cool, because if you get a forecast that there's a 92% chance you're gonna be stressed out tomorrow, just like if you know there's a very high chance that it's gonna rain, you can take an umbrella, maybe you can take some steps to help alleviate this. So you can go to that extra yoga class, get some extra sleep, whatever it is you need to do to improve your stress. And then the second thing that we thought would be really important, especially for populations that suffer from a lot of stress and are at risk of converting to depression, would be tracking their long-term history and potentially tracking whether they might transition to a depressed state. Because actually moods have been modeled as different stable states of a dynamical system. So healthy functioning is a stable state. Even if something bad happens, it perturbs you a little bit, you usually bounce back. But if you're in a very high-stressed environment or you're perturbed continually, you could actually transition to a different state, to depression, and then again, you're kind of stuck. Even if you're perturbed, you bounce back to depression. Yes?
Has any work been done showing the effects of telling people forecasts like this?
We are starting to investigate that. There are some very complicated UX questions around, is there, if I tell you that you're going to be stressed, is it a self-fulfilling hypothesis? Does it actually help you? How can these interventions be delivered in a meaningful way? So that's a really good question. But the main focus of my contribution to this work was on this piece. Like, how do we actually even get the prediction in the first place? So yeah, and so if we had those predictions also, even if we don't deliver this, it would be nice to be able to sense if someone might be on the wrong trajectory. So that could be really important. Okay, so how do we do this? Well, Akane and Sarah and a little bit me spent many years collecting very high dimensional data from students. So we collected their location, their physiology data, we extracted their steps, their temperature. We made them tell us everything they were doing. Did they go to class? Did they drink alcohol? Did they drink coffee? When did they do it? We looked at everything they're doing with their phone. Well, not everything, but who they're texting, who they're calling. So just a massive amount of very rich data. And we actually published just a ton of papers on this problem. Like, how do we use this rich data to predict people's well-being? We built whole online tools that allow people to upload their physiological data and to detect the artifacts in the data, detect the peaks. We made whole papers on dealing with noise in the data. So, for example, what do you do if a whole set of features goes missing at once? Like someone forgot to wear their sensor, or they don't want to turn on the location tracking. How do you cope with that missing data and still make a reasonable prediction? So we did all this work, but what we found is that the accuracy in predicting these outcomes, like for example in predicting happiness, was still disappointingly low. So this is a little too close to the horoscope side of the spectrum or mood ring side of the spectrum than the deployable system that could help detect depression in the real world. So why is this not accurate enough? And I swear it's not just that we are terrible at research. If you look at the literature, even in detecting happiness on the same day, the accuracy is pretty low. And we're trying to, of course, predict future happiness. So why is that so low? Well, the reason that we came up with, we thought a lot about this, is that these models are not accounting for individual differences. So we're training this giant shared machine learning classifier that's trying to say when everyone will be stressed. But actually people are very different in the way they get stressed. So for some people, they might be very happy at Friday night home alone coding, and if you put them in a loud crowded party, they're going to be stressed. Of course, for some people, it's the exact opposite. So these models currently were not able to account for these differences at all. So what we tried to do was to use multitask learning to get this personalization. So what we're trying to do is treat predicting the mood of each person as a separate task. And that allows us to customize the model to each person. But we can't train just 50 independent models for each person because we don't have enough data. So what we want to be able to do is still benefit from the statistical strength of the data of other people, but to the degree that they're related to each individual. So the first approach we took was this neural network approach. We had some shared feature extraction layers that we hoped would take this high dimensional data about every time you sent a text and compress it into something a little more reasonable that we could build on top of. And then individuals or clusters of individuals had their own layers that mapped that representation to how it would affect that person. The second model we looked at, one of the few non-deep learning models in this presentation, was a hierarchical Bayesian model based on a Dirichlet process prior. So what's happening here is we're drawing the weights of each person's classifier from the shared DP prior. And based on the Chinese restaurant formulation of the DP prior, that's going to induce an implicit clustering of people based on their decision boundary. So you're basically going to get placed in the same cluster with someone who reacts in the same way in terms of their stress as you do. And it's a non-parametric soft clustering, so we don't decide the number of clusters in advance, and people can actually belong slightly to several different clusters, giving the model more expressivity. And then the third model we looked at was a multitask, multi-kernel learning model. So what we're saying here is that we have all these different types of features, like physiology features and location features, and we're going to learn a kernel over each of these types of features, and then for each individual, we're going to customize the weights on those kernels. So how much is your physiology predictive of your mood? And we regularize those weights globally, and we perform an EM so that you gain information based on how other people are weighting those weights. So how well did this work? Well, we compare each of those models to their single task learning or traditional machine learning equivalents. So SVM, logistic regression, and neural networks. And we see that in single task learning, we still get pretty low accuracy. So very typical of the literature, not very performant. If we apply these techniques where we treat the different tasks as just the different related moods, we don't really see convincing performance gains. So it's not that the techniques themselves are solving this problem. But what we do see is that if we use those techniques to customize the models to each individual, to personalize, then we see very large performance gains, sometimes up to 20%. So at the time we published this paper, this was actually state of the art in predicting these outcomes. So we were very happy about that. But what's more interesting is to look into what the model actually learned. So these are the weights that the model is placing on the different features for each individual. And what we see is that for the stress model, these are all like stressed out undergrads from a certain institution. So we see that they're pretty much regularized to be quite similar. But for mood, it's very individualistic. So what we're seeing is that for some people, the weather is incredibly important to their mood. But for others, it's not really at all. So that's showing that we need this model to account for these individual differences. Similarly, this is one of my favorite findings. We actually looked into what this hierarchical Bayesian model learned in terms of the clusters. And we did a post hoc analysis of the individuals belonging to each cluster and looked at whether they differed from the group significantly in any way. And we see that cluster 0 doesn't differ significantly from the group. So it's kind of your standard person. Cluster 1 is significantly higher GPA and significantly higher conscientiousness. So they're more organized, they're more like on time, punctual. They have their stuff together. And interestingly, that cluster actually really enjoys routine. If their day is more likely under their normal day model, they'll feel less stressed. So we think of this as like our studious cluster, basically. This cluster, however, in contrast, is very highly extroverted and has lower physical health. So I don't know what extroverted undergrads are doing that's lowering their physical health. You can make some guesses. But what we see is that the extroverts, if they spend a ton of time on campus and they text a lot of people, especially late at night, then they actually feel less stressed the next day. That's a good day for them. But in contrast, the studious people, if they do the exact same thing, so they're on campus and they're texting a lot of people, they are much more stressed the next day. So we see that if we had lumped these people together into the same model, it wouldn't have been able to account for this difference at all. And if we tried to make predictions using these features, it would have washed out. So this personalization is really important. So we extended this to actually predicting people's, not only their binary classification of whether they were stressed or not, but actually the regressing on their stress level. And we did that with a Gaussian process approach using domain adaptation. So we trained your standard Gaussian process on everyone else's data. And then we used this domain adaptation approach to adjust the mean and variance of that Gaussian process towards the individual's data. And then for neural networks, all we did was just change the loss function. So deep learning is nice and easy. So then we see that these personalized models in terms of regression perform better for the large majority of the participants. And in terms of the model fit to the data, we see very vast performance improvements. So this interclass correlation not only accounts for the mean absolute error in predicting the outcome, but also how well it fits the trend of the data. So we see very large performance improvements there. So in conclusion, I've presented work on improving well-being detection with, and working with noisy data, improving multi-agent reinforcement learning through social learning from other agents, improving conversational AI with sentiment detection, and improving a generative model with facial feedback. Oh, wait, what does it say? Thesis proposal. Oh, right. That's because that's actually what I proposed to do. So, yay, I managed to get those projects done. And I really want to take an idea from my friend Juliana. She suggested to be a little more honest, though, about how hard these things can sometimes be. So my thesis proposal was very nice and neat. I was going to finish these projects in this order, and I was going to leave all of 2019 for writing my thesis. So things slipped a little and left only a couple months to actually write the thesis. And then I decided to do all my job interviews in those couple of months. So I would not recommend doing that. It's been quite a wild ride for the last few months. But we made it, so we're here. So in conclusion, the research direction that I really want to emphasize is that I think social learning is an incredibly powerful mechanism for human learning. So it allows us to rapidly adapt to new situations. It allows us to transmit knowledge amongst ourselves and build on that knowledge. And so I think not only can multi-agent systems benefit from learning from other agents, but that any AI system can benefit from learning from humans, because humans are smart, they know what to do, and they're the best arbiter of their own preferences. But in order to learn those from human social cues, you need to be able to detect them, which often it necessitates accurate detection of affective signals. So in future work, what I'd like to be able to do is integrate these two directions to training multi-agent policies that are able to coordinate quickly with other agents, maybe with new agents, and then generalize that to coordinating quickly with humans in these cooperative environments. So I think that could be cool. I also didn't get to fit all of the papers I published, so these are extra papers that didn't make it into this presentation. If you're curious, please let me know. And then, of course, I want to deeply thank everyone who's helped me with this thesis. So especially calling out my advisor, Roz, who's been incredibly supportive and an amazing advisor, and really giving me the freedom to pursue the research direction that I'm passionate about, which has been so important for me, having a happy PhD and enjoying myself. And also Doug Eck has supported me for many years. I met him in 2016, and when I was first starting to learn about deep learning, he's really helped my career. Nando has been incredibly insightful. I think he actually asked the question that originally spurred the causal influence work, and that ended up winning an honorable mention at ICML for best paper, so we were pretty stoked about that, so thank you so much. And Joel has been incredibly patient and amazing, and actually sat down with me and given me like deep technical feedback on like hyperparameter tuning and stuff, and that's like amazing of you, so thank you so much. And of course, I want to recognize all of my collaborators. So I've had a series of amazing collaborations, had the privilege to work with incredibly smart and amazing people, and I couldn't have done it without you. So I really want to call out Sarah Taylor, Azma Gandharyun, Judy Shen, Vincent Chen, Akane, Ehi Sakure, Prane Sano, Shane Gu at Google Brain, Chalar Gulshaher, I'm not sure I'm saying that right, but at DeepMind, Craig Ferguson has been amazing, Christy, you've been amazing, so I really want to say thank you to you. And of course, my parents would kill me if I didn't call out how much they have helped me, but they really have. My parents are incredibly supportive. Anytime something goes wrong in my life, they've been amazing. And I just want to, I didn't know how to write down their names in the right order, so I just want to call it that there was an equal contribution of both parents. My brother has been amazing. My grandma has always supported me. Mavis, Arlene, both grandparents. I've got Tiffany and my aunts, Linda and Bill, and Auntie Pam, Auntie Lana, so many more. So I really want to say thank you to you. And then, of course, my friends. So sorry you're sitting through a lot of sappy acknowledgements, but I have to do it. You guys have meant so much to me. Meeting friends here that we've been so close over the last 5 years is starting to feel like you're just my family. Like Christian and Juliana picked me up at the airport, which I think is like the real bonding signal. So I really want to call out thanks to Max. He's been amazing. Juliana, she's been my friend for so many years, such a sounding board for ideas. Christian and Juliana, so close. Andrew has, of course, been incredibly supportive for many years. And Bianca, Kelsey Allen is here. Thank you, Kelsey. Peter Bashai, couldn't miss. Eddie, Martin, Carolyn, Sam, Gavin. And of course, you guys won't get this, but I have to do it because these friends are actually really meaningful to me. I've done a lot of internships and spent a lot of time away from Boston and become really close with some people that couldn't be here today. So I do just want to call out Ben, Laurent, Kyle, Niru, Joanna, Tim, Anna, Yannick, Matthias, DJ. So hopefully if I send them the recording, they'll know that I acknowledge them too. And now at this point, I'm just making you looking at a bunch of sappy pictures throughout my PhD. So I'm going to wrap up. So thank you guys so much for coming. I really appreciate it.
I think there might have been a little social influence. Okay, time for Q&A live with our public audience here, and committee members are fine to ask things too. I should probably, since this is being recorded, pass around the mic also. So
I can also repeat the question, yeah.
yeah. Here. Neela, you pass it to the next person.
Got it. Amazing presentation. Thank you so much.
Thank you.
Really a treat. It strikes me that probably the most commercially valuable application is really just manipulating people on a massive scale and surveillance capitalism and all that. What can we all do to kind of make sure that everything that you're doing ends up helping people as best as possible, given that?
That's a great question. So actually, I really wanted to stay away from follow-ups of the social influence work that we're influencing people. I think that gets down somewhere dangerous really fast. But you should also think of the social influence work as a way to compute the degree of influence between two agents. So you could use it as a metric of saying how much someone was influenced by a given action. Potentially you could use that to detect whether people are being influenced and maybe intervene. So I think that could be interesting. And then in terms of the affective components, you can think about people's affective, the reason I talked about AI safety is your affective signals are changing, right? So if I make a joke to you and you laugh, and I make the joke again, you're not gonna laugh the second time. So there's this non-stationary reward signal that measures whether you're actually currently enjoying what's going on. And so if you were able to actually use, for example, reinforcement learning, which accounts for like total expected long-term reward, and you were really able to use that to account for your long-term enjoyment and like happiness and fulfillment and flourishing, well-being, which is something that our group has thought a lot about measuring, if you could really optimize for long-term well-being using these functions, and I think that would be a more safe AI model.
But you still need people in power to believe in that reward function, or people they don't always, unfortunately. By the way, if people want to follow up on that question, which is one I'm very interested in, I'm happy to continue to explore that one with you guys. Other questions? Joelle? Any? Yeah.
Or someone on the phone too is welcome to.
Yeah. Or Doug or Nando?
They might be muted. I think I see that they're
I
muted.
just unmuted. Sure, I do have questions. So first, that was an amazing talk and an amazing dissertation. And I sense there are some other PhD students in the room there. So I want to point out that Natasha set the bar at 14 research papers for a good dissertation. So the rest of you have a lot of work to do. Joking aside, so my main question, the one that I've really come away with asking is, what is social? And can we meaningfully talk about social in the context of agents only? Like, there's a nice bridge to build between, I'm thinking of the dissertation document, not the talk, but between chapters, let's see, 4 and 5, I think, 3 and 4. Oh, no, chapters 2 and 3. When I think about the work that we did together and the media generation work, the music generation work, when I think about two music agents jamming together, it's not clear to me that has anything to say about a human and an agent jamming together. And I'm wondering if you think differently, if you think there's something we can take from the literature of multi-agent work and apply it to humans. And then more generally, is that interaction among agents even something that we would call social, or is social embedded in the world and embodied in the world? That's my big question.
That's a great question. So I think there's definitely something there in the sense of like, can we even say that these agents have agency, right? Are we there yet? Probably not. But what those problems share and what the jamming problem actually shares is trying to infer another agent's intentions in order to coordinate with it. So if you're jamming with someone, you have to kind of understand where they're going, where they're taking this, how you can work with them in order to make that sound good. And similarly with the multi-agent problems, they do share that in the sense of like, if I want to coordinate with another agent to achieve some task, I have to infer what they're doing and try to achieve the other part of the task. And that also works with humans. So if I want to make a human happy, I want to please a human with whatever Alexa's doing, I need to infer what they want, infer their intention, what are they trying to get out of the interaction with the agent, etc. So I think this idea of like modeling other agents and understanding what they're intending and how to coordinate with them is shared across.
Agreed. Okay. That's my main question. I'll pass to Nando, I guess.
Thanks. Natasha, great work. I think this is a brilliant thesis, and I hope just the beginning of a very bright career. I have a few questions for you, and some are purposely hard. You mentioned it's a PhD, so you get to be asked these. You mentioned that, so one of the very nice things about your work is by having the influence reward, the agents were able to communicate better. So you were able to train agents that would communicate, excuse me, in a completely decentralized manner, which hadn't been done before. Like very good researchers failed at doing that, including myself and colleagues. And then you mentioned that one of the things you would like to look at is compositional communication. Mm-hmm. Why do you think that's important? And the other thing is, if you think of it as like a stream of, say, discrete symbols that can combinatorially be combined, mm-hmm. Why do we need that, and why can't we just go with a single continuous vector?
Yeah, that's really interesting. So I think in some sense you kind of answered your own question, like in saying that it's combinatorial. So with this small set of discrete symbols, which we know how to do really well with current reinforcement learning techniques, learn a discrete policy, we get this combinatorial explosion of things we could communicate or things we could talk about. So I think you always give this example of like, there's a village of 300 people. I don't have to talk about each one individually. I can group that. I can make categorizations with these symbols, and you can get the relationships among them. And why don't we want to go to continuous vectors? I actually think we don't want to go to continuous vectors, and we no longer want to use ungrounded discrete symbols either. Because I think while studying like the emergence of language language is really interesting. What would be interesting to pursue going forward is actually to try to go back to this idea of having agents communicate with human natural language. Because I think for the problems that I want to look at, it's not only can agents coordinate with each other and communicate with each other, but can they generalize that to actually coordinating with humans? So taking the same policy that can flexibly adapt to multiple different types of agents. And then you need this like grounded language in natural language so the agents can use it, but it can also be used with humans so they understand it. So that's why I think we should go that direction, rather than use continuous vectors.
All right, so you would basically capitalize on the fact that there's creatures on this planet that already have language.
Yeah.
So let's use the language in the channel to ensure that the agent somehow internally develop concepts.
That would be great. That would be amazing. Yeah.
So that brings me to your other work, which is on learning from trajectories of observations by imitating. For me, one of the best examples of imitation is, I forget his name now, the high jumper that in the 70s in the Olympics learned to jump backward as opposed to jumping forward. So up to that point, people had come up with all sorts of crazy strategies. That's just basically RL. And then what happened at that transition point is, so it goes that he was an engineering student who went and did a lot of calculations about the center of mass and so on and figured out that this is what he had to do. So if stories are true, then he used abstraction to be able to solve the problem. And since then, we've been just following straight imitations, stuff that is very similar to your BCQ or regularized reward maximization. So then this question of how to get abstract concepts seems to be very important to how we do better imitation. But do you think that having then just the language channel, that will be enough? Would there be a way of you testing that the agent, having acquired your RL agent, which started with this language by exploiting the language channel, was able to do some improvements over just the behavioral cloning policy that would show that it was exploring in this higher abstract space?
That's a great question. And I think the language model, as you said, might give you some clue towards concepts. And I think it actually might give you a nice path to generalization. So if I give you a command that you haven't exactly seen before, but is close in embedding space in the language model, then I could infer what you're talking about in the environment. I think that's cool. But I don't know if it would get us all the way there to like, if I have a trajectory of low-level actions, abstracting out high-level goals. Like, what was this person intending to do? And of course, like, conditioned on a goal, the low-level actions could be quite a bit different. Right? And so different people might take the same goal and actually enact it very differently. So I think there's kind of an unsolved problem there in terms of like segmenting a trajectory into these high-level goals. But I think it would be an interesting question to pursue because you can kind of think of this high-level goal that the person is pursuing as their intention. Like, what are they trying to do? Like, if I observe, it goes with the multi-agent learning piece, right? So like, if we're trying to coordinate to make some recipe, one of us has to get the tomato, one of us has to get the lettuce. If I observe your low-level actions, I need to infer that you're getting the lettuce so I can get the tomato. That's sort of like inferring this goal. So I think they kind of overlap.
Thank you.
Thanks.
And I have two more questions. They're sort of more like nitpicking. So
Okay.
your reward function for that project, it involves a lot of small numbers with like 3 digits and so on.
Okay.
I forget the page on which it is, but it's 0.157 times the question plus 0.138 times the semantic coherence plus 0. And so on. So it's this very. Is there any hope that instead of like building a reward like this, that you could use something like, say, generative adversarial imitation learning to learn a better reward?
I think that's a really
Or
promising
one that-
direction. Yeah. Because so the reason those numbers are so small is, by the way, we're just normalizing so everything sums to 1. But yeah, I think that's a really good point. I don't think those rewards are the final answer. So we saw that our agents were moving towards, yeah, more polite and cheerful language, but we don't know that that's actually a better conversation. There's a lot more richness to what makes a good conversation than those signals. So rather than sort of handcrafting that, you could also think about some type of like inverse reinforcement learning, observing people talking to each other that do have a good conversation. Of course, I have prior work on inferring what is a good conversation. So then look at the good conversation and say, what is it that people are enjoying about the conversation? How do those conversations look? And try to get the reward function that way, yeah. But I think there's definitely a lot of future work to be explored there, for sure.
And the last question has to do with, so there is this beautiful cycle of for doing RL from demonstrations, which is you can learn the policy completely from data, as you have shown here. You can learn, we could potentially learn the reward from data. The other thing we could learn from data, perhaps, is how good, or at least from very few interactions with environment, is how good is the policy before we deploy it.
Yeah.
So you mentioned in some cases it will be catastrophic. You deploy your dialogue agent on Twitter and it says a lot of obscene things and you're in big trouble, so you get fired for that.
Yeah.
But in some cases, it's inevitable that we will deploy a policy and there will be some adverse effect and we might have to re-update that policy.
Yeah.
And so how could we learn from the experience to design a better agent?
Yeah, so that's there's a whole rich field on off-policy policy evaluation that we were looking into a little bit because it's related to this paper. So you can use things like importance sampling to reweight samples so they look more realistic under your current policy. And I think that is very important. But of course, the question is, like if you're deploying to humans, are you able to actually foresee this type of inappropriate behavior? Or is that sort of like extrapolating off what you even intended? Like, you know, in some sense, you kind of have to model that that's a region of state space to anticipate that the policy is going there. So I think, I mean, for me, maybe this isn't a very machine learning-y answer, but you kind of need some kind of human in the loop to assess whether this is actually safe and appropriate to release. Yeah, so it's a complicated question, yeah.
The question I guess that I was trying to get at is once you've released and you discover it doesn't quite do what you want,
right.
How can you learn from that to update your policy?
Do you mean like iterating on the reward function or iterating on what it's trying to optimize? Yeah, I think that's really important, right? So an ongoing way to, so maybe you're saying there's this iterative process of like inferring a better reward using like Gale or using inverse RL, retraining, redeploying, and continuing in that way. Yeah, cool. That seems like a really good idea, yeah.
Thank you very much. No more questions.
Mando here.
Hi, really great presentation. I just have a very general question, which is specific to, I guess, your end goal or your future steps. Very broad. What do you think could be the next set of next steps for tackling this problem of social intelligence? And I'm in particular really curious about what led you to reinforcement learning, specifically model-free reinforcement learning, for handling the problem of multi-agent RL or multi-agent settings. Do you think, what in your mind are the limitations of using RL as a solution framework for handling those types of settings? You meant, I mean, already from the presentation as well as from the Q&A, you sort of get this feeling of there's a problem of reward engineering. There's a problem of like, you know, defining what is a good reward in order to get some qualitative good policy, or, you know, using, after you trained a policy, you noticed that they were using some sort of navigation policy as a way of communicating other intentions, right? Like, there's a lot of really interesting conceptual frameworks that we're building on top of what we train on in a model-free RL approach. And I'm curious about, given all of the work that you've done putting into understanding social intelligence and modeling it, what are the limitations and what do you think it should be the next step forward? Should we stick with RL? Or maybe is there another framework in the works of, you know, taking us in the right direction, if there is a right direction.
Sure, thank you. Yeah, so I would say, firstly, I'm not in love with like model-free RL. I don't think we have to limit ourselves to that, and actually what we saw in the influence work is that having a model of other agents was critical to doing this well. So modeling the world seems like a nice way to integrate extra information, and you can use other techniques like unsupervised learning, and that's also in the dialogue project. We first learn unsupervised a decent model of conversation. Well, decent is we're stretching the term there, but we try. And so I'm not wed to that, but I do think RL is really promising, and I'm really excited about it. And basically for two reasons. So the first is that RL is a super broad paradigm that basically describes the scenario anytime an agent is interacting with the environment, taking actions, and getting feedback. So it's this idea of like not static learning, but actually doing this interaction. And so it's so broad that it seems like it's inevitably going to describe whatever we want to do with AI, whether it's a conversational AI, whether it's a robot that's in the environment, it's going to be interacting, and you want it to be able to learn from that interaction. And the second thing about this is that, I don't know if you've seen this very well replicated work that shows that dopamine neurons in the human brain are actually encoding a temporal difference signal. Actually, Nando pointed me to this. They're encoding a temporal difference signal that's a fundamental component of RL. And so I think that's a really promising clue that we're kind of on the right track. And yeah, just this optimization function of estimating total expected future reward, long-term payoff. I do this action now, but I don't want to be greedy. Like, how will this actually work out in the long run? That just seems like a really promising framework for something that our agents are going to want to know about the world. So that's why I like RL. Yeah.
Thank you.
Thanks.
Thanks also, it was great presentation. The question I have, you mentioned about categorizations of like different agent and personalizations of them.
Yeah.
So I'm wondering like if you can also frame that in the problem of like model-based and how you can find the optimal like policy when I know like what is the differences between different agent or like characteristic of different agent, how I can have like optimal like interactions with them. Like have you considered that or like what you like perceive?
Yeah, I think that would be super promising. So if you had some model-based approach where you basically could distill people into some latent characteristics of people, and then use those latent characteristics, for example, to condition your RL model so it has a sense of like who it's talking to and how it can adapt to that person. I think that's really promising. And then you could even do something more interesting where your RL model observes some feedback that actually that person didn't like it, so you've miscategorized them, so could it update your extraction of the latent factors? That could be really cool. Yeah. You guys are giving me so many good ideas.
Thank you. Let me ask a few questions.
Yes.
And first start by saying it's been an absolutely pleasure to see the progress of this research, and in particular seeing you engage more and more deeply with some of the technical models and technical questions arising, still not losing perspective of the application side of things. So from that point of view, I think, and maybe reaching back to one of the previous questions, some of your contributions are around this concept of intrinsic motivation and what that means in terms of reward function. And you go through an interesting mechanism, and you're not the only one, a lot of the literature does too, to sort of take intrinsic motivation and turn it into explicit reward. Right, in this case, by like labeling different emotions and essentially giving a valence, positive and negative, to these. And so I'm left a little bit with this interrogation of, should we be skeptical that there is a useful notion of intrinsic motivation, right?
Yeah.
Isn't it the case that we may be labeling some of these things intrinsic, but at the end of the day, there's no learning without a loss function. And in RL, there's no reinforcement learning without some notion of a reward. And the only way to get to that is to have human input on that definition.
Yeah, that's a really good point. And I think there's kind of a blurry line where you could get into a situation where you're actually doing quite a lot of reward engineering and still calling it intrinsic motivation. So maybe broadly, people do have an intrinsic motivation to get along with other people or have empathy. But like, at what point does it actually just get into like hand engineering something for a particular domain? And so yes, that's a valid criticism. Do I think there is actually a concept of intrinsic motivation that is meaningful, I would say yes. I think like the work in curiosity is really promising. I do think humans have intrinsic motivations like curiosity, like empathy, that help drive us to not only learn but coordinate with others. I think the direction of like self-supervised learning is a promising one that does seem like the agent has to have some intrinsic thing it's trying to optimize. It's not necessarily an externally imposed goal, but it's a way that it can learn. It's a way that it benefits from learning from interacting with the environment. So do I think the concept is useful? Yes. Do I think every implementation of it is deeply generalizable to many different environments? Not necessarily, right? Yeah.
And I'm going to ask another question that deals a little bit with this notion of reward, but a little bit more with the work that you've done on off-policy learning. Mm-hmm. And so one thing that's interesting here is the space of actions that you considered mm-hmm. for off-policy learning. Am I mm-hmm. right in understanding that it was actually at the level of
the word
choosing the words?
Yes.
Right?
Yeah.
So this is very interesting because it's an action space that is much higher dimensional than most of the action space that are considered usually for off-policy learning. Mm-hmm. Is there something we need to do differently when we think of off-policy learning in small action space versus large action space? Because in your case, you sort of, you lined up, there's these previous methods, and here's a few variants that you've explored, mm-hmm. but you didn't necessarily lean into the complexity that arises from having a very large action space and what that means specifically for off-policy learning. So what are your thoughts on that?
Yes, so I think there is definitely something that you have to do that's very different. And one thing I mentioned is that you have to have a reasonable pre-trained model. Otherwise, this overestimation issue and this extrapolation error issue would just be catastrophic. So you absolutely have to be bringing in some prior knowledge to give you some way to start over which of the words you could emit. And so that is quite complicated. And then the second thing I would say is that it's not the only answer to doing this. So we're currently looking into, as you saw it, it's a hierarchical model, right? So we're actually currently looking into controlling the model at the upper level of the hierarchy, like the sentence level of the hierarchy, because we think that could reduce some of the complexity and allow the model to sort of choose conversational goals that it's conditioning on. So that's a future direction I'm thinking of.
Is there a notion at which that helps you get a better sense of like the similarity between the spaces? Because one of the things in off-policy learning is trying to relate the space explored by your behavioral policy versus your target policy and relate that in some representation. Do you think that gets at the question of how to have a lower dimensional latent representation between these things?
So I think the thing about doing this on the word level is that it's going to be really hard to do credit assignment and propagate back the correct choice when you have so many words in a conversation, and each time you choose each word you have such a broad action space. So doing credit assignment at the word level is going to make less sense than doing credit assignment at the sentence level, because that's closer to getting at like what is the conversational intention of what I'm trying to say. So I think that makes sense.
And so that handles both the dimensionality of the action space, but also the sequence length, which is also probably longer in your cases than some of the previous ones.
Yeah.
Excellent. I'll ask one last question, perhaps for the benefit of the audience, is more than yours. Looking back at that thesis, if there's one piece or thing that you wish you would have done really differently, what would it be? If you had the benefit of like 6 months to...
Yeah, well, there's many. So I guess like immediately what popped to mind is that there's whole projects that I spent like a year on that didn't make it into the thesis. Like I wrote a whole journal paper on like a UX problem on behavior change that we just never submitted because people dropped out of the study. There was too much attrition, and then I wasn't very happy with the paper. So even though it was written, we just never submitted it anywhere. So those are things I would have done differently, like the work that got dropped on the floor. I guess one thing that connects a lot of the things that I wish I'd done differently is giving myself more time to do a project in great detail. So I think we talked about how I actually think the dialogue project is a little bit premature. Like we put it out because I'm graduating, I have to wrap it up, but I would have loved to spend another 4 months on that and really dig into it and improve some of the models. So this has happened multiple times where I haven't given myself enough time to finish a project. I was doing this whole Gaussian process thing, I didn't finish it. I was doing this whole curiosity thing. I had to go to an internship, I only had 2 months, and I had to sort of drop that project behind. So basically, giving myself more long-term time to really finesse a project, because I think it makes more sense to put out fewer really impactful papers than just churn out papers before they're ready. So, yeah.
Thank you.
Yeah. Hope Juliana likes that answer. Yeah.
Natasha, can I jump in with one more quick question?
Yeah.
I thought we were going to go round robin, so I only asked one question and then passed off, and all the rest
It's okay.
of it.
Yeah.
So I actually don't have a lot. My because there's been a lot of ground covered, but there's something that you just said sort of triggered like. So you just said you need a pre-trained model, right?
Yeah.
Right. Like, I'd hoped that, like, my hope is that we don't need pre-trained models, right? Like, there's something sort of so. The thing that I like the least about model-based reinforcement learning right now is so much of this work is kind of like doing having one model and then dropping it in and kind of fine-tuning it on a problem, or like I have this sense that there has to be an integrated way to think about reinforcement learning and gradient descent learning, and that we're sort of halfway there with model-based RL, but we're not all the way there. And it's not just wading through the math. There's sort of a conceptual leap that we need to make that allows models to learn from non-differentiable reward and from some differentiable signal. But we're not going to get there with like dropping like, here's a pre-trained RNN that does thing Y, and then we're going to drive it with so like, if where do you see the research going in this direction of trying to unify this world, or do you think I'm wrong? Maybe I just don't understand enough about the beautiful elegance of model-based reinforcement learning.
Well, I definitely wouldn't say that you don't understand it, but I actually think, well, let me first say, since we published Sequence Tutor, there's been a lot of work that actually integrates learning with RL and supervised learning at the same time. So I was talking to some machine translation at Brain Montreal people that were enlightening me to this, and why not just do this simultaneously? So I think there's really something in what you're saying there. But actually, I really think the promise of deep learning is this representation learning promise, and why it's been so vastly successful is you can take a whole bunch of data that you can just scrape from the internet, just scrape every web page that ever was linked to from Reddit, build an amazing representation, and then plug that into so many downstream tasks and either continue learning on top of it or just leverage it. And because you can just connect these things like Lego blocks and back propagate gradients into your pre-trained model, I think that's just so powerful. So I think if you say you could never pre-train and plug in, you're like erasing a lot of the benefit of like doing this representation learning.
Well, no, I mean, I have this faith that we can understand more about how organisms learn, which is by pushing the world around and interacting with the world and learning from that interaction.
Yeah.
And, like the sample inefficiency of like training on, I mean, sure, we can sort of slurp up this huge language model of all of the internet.
Yeah.
But I still carry a certain cognitive science part of me that says we should still at some level be inspired by how humans learn, as definitely not what babies are up to.
Well, I mean, that's a question. Do we have a full understanding of what babies are up to? I'm not sure. So I think Nando would say this.
Okay, partial understanding.
But yeah, okay. I think Nando's point, which I really like, is that we still don't have a model that has trained on the richness of a baby's experience from the time it's born to like 5 years old. Like not only all of the experience of manipulating the world, viewing the world, hearing language, as well as audio. Like we haven't integrated all those signals, and so we don't have a perfect way of doing that. But I think a promising way to actually integrate those two pieces of knowledge is to not only let a model like manipulate and interact with the environment, but maybe integrate a really powerful language model into that and maybe align those representations. If you had an alignment of language understanding with acting in the world, it seems like then you could get to something that could be approaching something really general, right? So I think it wouldn't make sense right now, maybe it's not the final end game, but it wouldn't make sense right now to throw away the idea of like taking this really good language model, for example, and building it in.
Okay,
yeah.
Thanks.
Your question actually about not wanting a pre-trained model made me think if we had a human learning person on your committee, they would say, well, that's 20,000 words. Nobody starts with 20,000 words. They start with fewer.
Right.
So do you think you could start without the pre-trained one when it's fewer, and then you get pre-trained, then that becomes the pre-trained one for the next one. And there's a whole developmental process there.
Yeah.
And how different would that be from what, you're doing here?
Yeah, that would be a really interesting and challenging like scientific problem. But I think you could do that. So having this curriculum of like learning in a really restricted set how to use language, generalizing that to a little bit more of a broad domain of using language, building in words, and seeing maybe how the learning looks different under that scenario than just instantly having this action space with 20,000 dimensions and training on all this language. And so maybe that's something I could pursue in the future projects I'm thinking about with these multi-agent scenarios where agents are communicating about what to do in the environment. We could restrict the the word set to be very related to the environment and then maybe expand
Which
it.
becomes like an expert in a subdomain or something
Yeah.
in the exchange.
Yeah.
So I want to end, because I'm going to end on one last question, and ask you what you think your thesis or your work on your thesis, just your own reflections, might tell us about how we could improve human learning.
Oh, interesting. Yeah. Well, I guess maybe affect sensitivity would be really important. Empathy is really important for human interaction. Like actually trying to, put yourself in the shoe, like not that my models are at all doing this, but like put yourself in the place of someone else and do that perspective taking, trying to model their intentions and trying to coordinate with them on that level. And basically also like sensing that using affective signals as a way to update and understand like what they're really trying to communicate or what they're really trying to do. Yeah.
Okay, I know there's still a lot more questions, but maybe you'll get time to catch Natasha in the what will hopefully, I think, pretty clearly be a celebration afterwards. Thank you so much, Natasha, for fabulous presentation.
There's going to be ice cream.
There's going to be ice cream.
If you hang
it will
around.
be in the affective computing area back there
Yeah.
afterwards.
Okay.